Every day, the future's getting closer.
Welcome to Master the NEC, where we talk about the National Electrical Code and all things electrically related. My name is Paul Abernathy, your host, and welcome to today's podcast. Well, hello everybody. Welcome to Master the NEC. My name is Paul Abernathy, and as always, thank you for taking the time out of your day to listen to our podcast. Today's episode is a part 2 of a multi-part series talking about transformers. Obviously, we have a video series on this that covers a lot of the details, but I've been requested to do a podcast version of this series in order to be able to talk about some of the topics that are maybe less able to show in a graphic and maybe more verbally you can get an understanding of the concepts. And we're assuming that you're building on to your knowledge, that you already understand the basic concepts of transformers. Now, I do encourage you to go back to listen to part 1 of this series because we talk about some real distinct fundamentals where we explain that when you're dealing with something like line current, when you're dealing with a delta, the line current doesn't match the phase current. Whereas in a Y configuration, the line current actually matches the phase current. And of course, when we're dealing with line voltage, remind you that in a delta configuration, the line voltage matches the phase voltage. However, in a Y configuration, the line voltage does not match the phase voltage. So that's a distinct difference when we're dealing with deltas in Y transformers. Okay. So in today's episode, we want to build on where we left in part 1, and that is I gave you an example of how to calculate or obviously how to configure and the aspects of a transformer, but I also went into how to calculate the maximum unbalanced load on a Y configuration. Okay, and I gave you this formula. And the formula that I gave you was based on the fact that we had current on each phase. And that meant that these was our neutral currents on each phase. And I kind of gave you that and showed you how to go through the formula. And it was a pretty extensive formula. Hopefully you go back and listen to part 1. But now we're going to put this into real world scenario where we don't always have neutral loads on each one of the phase. So we want to, because we have different loads. We have some 3-phase 208s, we have some single phase 208s, and we have some single phase 120s that we're dealing with, and how that kind of works out in the real world. And so that's what we want to talk about today. So we're going to talk transformer balancing. Now, here's something to remember. That when you're balancing a panel or you're balancing out the transformer, it's essentially done the same way. We need to determine what our VA is rating of all of our loads. And by taking that, then we can start working through a step process to determine how we're actually placing these loads on each winding of the transformer. And that's what we're trying to do, because a transformer, for example, if I was dealing with a 90 kVA transformer, then typically what I'm going to have is a 30 kVA winding, and I have 3 of them. So there are 3 individual single phase windings that are put in a configuration that gives me 90 kVA. However, we are limited to the 30 kVA per winding. So that is certain things that you have to understand, fundamental basics. Now, in this episode, we are not going to talk about what happens in a delta where we lose one of the windings and the ability to be able to have a certain percentage of the 2 of the remaining windings to be utilized and things like that. We're not getting into that, okay? We're not getting into the potential of a failure of a transformer. We're getting into the concepts of how to deal with transformers, how to size transformers, and what you need to know for an exam, for example, or practical real-world scenarios. So in this case, the first one we're going to talk about is a Y transformer balancing. So it's a delta to Y transformer. Very typical, a 208-120 secondary. Typically, we want to use the 120 for all of our lighting loads or all of our 120-volt loads because we have 3 separate windings to be utilized here, whereas on a delta secondary, where you're center tapping the C transformer portion, then you're basically line 1 to line 3 center tap. You only got half of the winding to use for your 120-volt loads. So in this case, if I had a lot of 120-volt applications, I might have 480 volts in the building, but now I want to step it down to a 208-120 in order to be able to utilize maybe a evenly distributed 120-volt loads, and I can get more of them out of it because I have more winding to offer for those loads, right? So there's an application for which transformer, and there's tons of configurations, delta to delta, delta to Y, Y to Y. I mean, there's different there's Y to deltas, all different types of configurations to whatever your need. We're going to assume that the engineer knows what they need for their job. Also remembering that some transformer are designed to reverse wind wire. And again, we're not going to get over what the ratios are. That was in part 1. So if you don't understand what a 2-to-1 ratio is or a 4-to-1 ratio transformer setup is, you need to go back and listen to part 1 because we go into extreme detail the ratios, the turns ratios when it comes to transformers and how it correlates to the relationship from the primary to secondary. Okay. So if you're just coming into this podcast and this is the part 2 of the series, I would recommend that you pause it and go back and listen to part 1 because I don't want you to get lost in the concepts here. All right, so we're going to balance out this transformer. Now I'm going to give you some loads. So you want to write these loads down because we're going to need these loads in order to determine. Now, the difference between what we did in part 1 is we took all of those loads as if they were all neutral loads and we calculated what the maximum unbalanced load would be on that neutral. In this case, not all of our loads are going to be on a neutral. They're not all going to have neutral loads. So I'm going to show you how we do it when we balance out a transformer. And incidentally, this is the same configuration on how you would balance out the panel as well. Now, when we balance out a transformer, that is so that the engineer can design the properly sized transformer based on each phase. Okay, and you'll see kind of how that works out. Now, we're going to do some rounding here and take that for granted that when we're sizing this, a few decimal points here or there is not going to make a difference in this scenario because we're either going to have to be stuck with a certain kVA transformer anyway based on what our output is, and usually never going to equally correspond. So just keep that in mind. I just want to get you into the concepts of how we do this. You can agree to disagree. If you disagree with me already, I suggest that you turn it off. Don't move forward. Why waste your time? Life is too short. Don't waste your time listening to me if you don't agree. Okay. Now, when we're balancing the transformer on the Y, we're going to go through a 4-step process. Okay? Now, I'm going to give you some loads. Write these down. We're going to have one load that is 42 kVA, and that is a 3-phase, pure 3-phase. It's going to utilize A, B, and C legs, and that is 208. Okay? Next thing we're going to have is we're going to have two 12 kVA loads, and those are going to be single-phase 208. Okay, so that's going to be connected between A and B and B and C in order to be able to achieve that load, okay? And then we have, lastly, we're going to have 3 individual 4 kVA single-phase 120-volt loads, okay? And it could be anything. So this is typically could be lighting, for example. All right, the 2 that are the 12 kVA single-phase 208, they could be 208-volt motors, if you will. Single-phase motors that are operating at 208. The 42 kVA 3-phase 208 could be a heater for some reason, okay? And that's just a lot of resistive loads that is causing us to have 42 kVA. Whatever it might be in your load, they're all going to result in a kVA value. And you're going to break that down. Okay, so let's kind of go through it. So the first step always is what we've already done. We have determined what our VAs are. And in this case, we're expressing them in kVAs. Okay? So we've got it. All right? Now, the second step. When we're dealing with it, we always want to start with the load that's going to be distributed evenly amongst phase A, phase B, and phase C. So of our options here, the 42 kVA was the only one. So it is 3-phase, so it actually is going to utilize A, B, and C. So the one I usually tell people is write this down on a paper. You'll have 3 columns. You'll have a phase A column, which results in your line 1. You'll have a phase B column that results in line 2, and a phase C column that results in line 3. And we're going to put some values under each one of these. Okay? So let's start with the one that's going to utilize purely the 3-phase application. And that was the 42 kVA. Okay, so you got your calculator out. What we're going to do at this point is we're going to take the first thing it says is we want to split these 3-phase loads evenly amongst A, B, and C. So we're going to have a third on A, a third on B, and a third on C. So 42 divided by 3 is 14. So in my column to the left, I'm going to write the loads. I'm going to have 42 kVA, 208-volt, 3-phase. Maybe I'll use the 3-phase symbol. And under phase A, I'm going to put 14. Under phase B, I'm going to put 14. Under phase C, I'm going to put a 14. Now, that 42 kVA load is evenly balanced across A, B, and C. Okay, so we've established that. There's no neutral loads involved in this. Purely, the application is split across each one of these phases. Okay, next. And we're not going to get into all the what if world is burning up scenarios and the sky is falling. Look, I'm preparing you for an exam, okay? And preparing you to understand the concepts of how we might balance out a panel, okay? Little bits here and there are not going to make that big of a difference, trust me, okay? Again, you can agree to disagree. If you disagree, there's that little button there that says stop. You can always hit it. All right, next. Next thing we're going to do now is we're going to work from our loads now that's going to utilize, instead we're not on the 3-phase, now we're going to utilize ones that utilize at least 2 of the phases, okay? And that would be the 2 12 kVAs because it is single phase, but it is going to utilize a phase A and B, and it's going to utilize a B and C. So how do we do that? Well, we're going to split the single phase 2 8-volt loads, and we're going to start with the largest to the smallest. In this case, both of ours are 12 kVA, so it doesn't really matter. We're going to put one half of it on phase A and B, and we're going to put the other half, B and C, and then we're going to put in on these 2, and then lastly, we're going to go A to C if we had a third one. Well, we only have 2. So how do we do this? Okay, so 12 kVA divided by 2 is 6 kVA. So I'm going to put 6 kVA under phase A, and I'm going to put 6 kVA under phase B. That's one of them. Now I've got a second 12 kVA. I'm going to put 6 under B, and I'm going to put 6 under C. So as you see, I distributed between A and B, one of the motors, or whatever it would be that's the 12 kVA, and I distributed the other one under B and C. So they're evenly distributed, okay, throughout the thing here. So, all right, at that point, it brings me to this. A lot of times, and if you listen to part 1, you understand that it usually doesn't result in the kVA being exactly that value of 6 when you're dealing with the situation where you have the 208 single phase. It usually is going to be a little higher. So I usually tell people if you're dealing with something between 15 kVA to 20 kVA or less of your loads that you're going to be doing this divided by 2, that you might want to add an additional 2 kVA to the values that go into column A and column B and column B and column C, because it doesn't work out exactly that way. And I just want you to understand the way that it works out. It could be an issue. And so since it could be an issue, we want to equate a little bit more VA on that, okay, in order to be able to do that calculation. So in my case, I might have it put it at 7 on A and 7 on B. So I'm actually taking this one as if it was a 14 kVA versus a 12 if I'm dealing with this situation. But let's just keep it at the values we have for calculation purposes and the ease of working through our calculation. We're going to work at this because I'm going to tell you that the little values are probably not going to make that much of a difference when you're selecting the overall kVA of this transformer. It shouldn't make that much of a difference, okay? All right. And it could be. It could put you on a borderline, but I just need you to understand that in some cases, you're not going to get an even division. In other words, a 12 kVA divided by 2 is 6. But when you're dealing with single phase 208, because of how they're out of phase, it doesn't necessarily give you an even split, if you will. Okay? So just keep, those type of scenarios in line. All right? Okay. So we're going to use 6 in A, 6 in phase B, 6 in phase B, and 6 in phase C. That's our 12 kVA distributed between A and B and C. All right. Now, in your column, at this point, you should have column A, which is phase A. You should have a 14 and a 6. In column B, you should have a 14, a 6, and a 6. And then in column C, you should have a 14 and a 6. Okay? So at this point, how is the kVAs distributing across, before we even get to our 120 volt loads, how are we distributing across it? Well, the 6 and 14 is 20 kVA so far on phase A. We have 26 kVA so far on phase B, so a little bit higher on phase B. And then on phase C, we have 6 and 14, so we have 20 kV. So A and C are pretty balanced. B is a little higher. So maybe at this point, we're not going to put anything else on B. We're going to look and see now where we're going to distribute our phases when it comes to our KVAs, when it comes to the 120 volt single phase application. Okay? So that brings us to the next step. So when we get to step 4, we're going to place the 120 volt loads. We're going to always start from the largest to the smallest load and work our way down. And we're going to put it 100% on any phase. But remember, we're trying to balance these out. So we might not literally put it, because some people would say, well, why don't you put, since there's 3 of them, why don't you put 4 kVA on A, 4 kVA on B, and 4 kVA on C? Well, we want to get it as close to balance as possible. Okay? And I'll show you how that works out. So now let's do that. So I have 4 kVA. I'm going to put 4 kVA in phase A. That takes me up to 24 on K6. And I'm going to put, since I already had 26 on B, I'm going to leave it alone. And I'm going to put 4 on C. Remember, we have 3 of them. So now it brings that one up to 24. Both of those are still less than B, which is at 26. I don't want to put the 4 on the 26 and then take that up to 30. And then I got 30 on B and I got 24 on A and B. I think I can balance it out a little better. So what I'm going to do is I'm going to put 4 more on phase A. That third one, that last one. So then that's going to give me 28 on phase A. It really wouldn't matter if you put it on C or A. But I've got 28 on phase A. I've got 26 on phase B. And I got 24 on phase C. That is about as balanced as I can get it. Okay? Across the board. All right? So that would also equate in what I do in the panel as well, and how I configure my layouts within that panel in order to balance out these loads, because each one of those lines that are coming into that panel is resultingly going to be putting that load draw onto the phase that it's connected to. And that's what we're doing here. We're trying to balance out the load that's going to be applied to each one of these windings within that Y secondary. Okay? Now, once we've done that, we can utilize that information in order to size our transformer. In our case here, we can simply add across the board to see what the minimum so far we would need. So I had 28 on phase A, plus 26 on phase B, plus 24 on phase C. So that's 78. Well, in this case, I probably would choose a 90 kVA transformer, because I need to make sure that one of the windings, especially phase A, is going to at least be able to handle the 28 that is being imposed on it, because that's what we designed it at. So I'm going to probably use a 90 kVA, and I've got some room there for some capacity. And I have to balance that out. When I go adding additional loads later, the engineer has to take that into account in how they configure those loads in the panel. So they have to have a fundamental understanding of how the panel load balances and how it correlates to the transformer balancing. And that is, again, for a Y secondary application. Now, in my previous podcast, part 1 of this series, I told you about how to calculate the maximum unbalanced load on the neutral conductor, and I gave you some fixed values, and those were 120 volt values, and that's pretty simple when you calculate it out. But in our case here, we're a little different, because the only 120 volt loads that we're going to be imposing on that neutral is really those 4 kVA single phase 120 volt loads. And they were only applied to phase A and phase C. In fact, we only have 8 kVA on phase A of neutral loads, and we only have 4 on phase C. So when we're going to do our formula, and if you remember the formula, it's not a complicated formula, but it is one that's going to be difficult for people to remember. Okay, so don't try to remember it. I usually tell people, jot these things down in your code book. Now, if you're taking an exam, like for example Texas, and again, disclaimer, not all testing places around the country are the same as Texas. Texas allows you, which is a PSI, and again, PSI lets each state develop their rules. So you need to check with your administrator of wherever you go to take your exam. Usually you can download a bulletin that'll give you this information. But for Texas, for example, you can make notes in your code book. So I usually teach people that back in the front where you have the code making panels, that you use all that blank area in order to write down different types of formulas through your career that might be beneficial to you. In my code books, I have all kinds of formulas for transformers, the transformer triangle, the transformer ladder. I have efficiency calculations, power loss calculations. I have everything in the front of my code book, because when I teach a class, I teach these formulas and I get people to write these things down in their book, because sometimes the classes I teach aren't just for exam. I teach engineers. I teach electricians that are going to go from a master's to further on, and like for the CMECP program, Certified Master Electrical Code Professionals, whatever they're going to do. Or maybe they just work for a company where the owner of the company wants their lead people to be more knowledgeable than the normal everyday master or the normal everyday journeyman. But that doesn't stop you from learning all these formulas. But there are a lot of formulas here. So I usually write them down, okay? Hey, my memory goes as well as I get older, so I have to write these things down. All right, so let's go on and do it now. Let's go on and figure out what our maximum unbalanced load is. Because, again, we have to size our neutral based on that. Now, we know that our neutral can't be less than what's required in 250.102C1, and we get references to that in 250.30 for sizing the secondary, the neutral, and things like that. And we have a lot of rules that we have to deal with in the code when it comes to grounded conductors, neutral conductor sizing. But we always have to remember that it still has to be handled to handle the load that's going to be imposed on it. Now, we might have some minimum sizing, especially when we're paralleling neutrals in 310.10H. We have to remember that if you're paralleling a neutral, and yes, you can, it can't be less than 1 aught. However, I am able to truly parallel a neutral. Okay, so you need to understand the concepts on how to do that, and maybe we'll have a separate episode for how you do that. But in our case today, we just need to find out what size neutral we need to at least handle the unbalanced load. And that's an important thing to take into account, especially when we're sizing everything. There are many cases where people will oversize a neutral, okay, because they might want to have what's called a 200% neutral. Maybe they're dealing with something that's going to have high harmonics and things like that, triplet harmonics and whatever, that type of scenario, who knows? So you always have to take different scenarios into consideration. But right here, we're going to show you the basic formula on calculating the maximum unbalanced load using the formula we talked about in part 1 of the series. So if you don't understand that formula, you need to go back to part 1. So let's talk about it. Again, we're dealing with OI. So the formula is the square root of the line current for line 1, okay, squared, plus line 2 current squared, plus line 3 current squared, minus line 1 times line 2, plus line 2 times line 3, plus line 1 times line 3, okay? So we're going to take all these values in the first part and do it to the power of 2, and basically it's take its ampacity and multiply it by itself. Okay, or you have a shortcut on your calculator or whatever. You can do that. So we're going to do that here because we need to calculate what this maximum unbalanced load is going to be in our scenario. Okay, so let's do it. All right, the first thing we need to do is figure out what we've got. So the first one in this said line 1 squared. Okay, so in our case, we have to calculate out what the amps is. So if you remember, we'll do that. We'll do a little calculation here and calculate it out. So what's the line current? Well, we know that since we're dealing with the line current in phase A, we've got 2 4 kVAs on it. So that's 8 kVAs. Since it's a line, this line 1 is a 120 volt line. So we take the 8,000, again, that is the 2 4 kVAs, and divide it by 120. That gives us 66.6, and I'm going to use 67 for our calculation. Okay? So that's the first one here. Then it says plus line 2 squared. Well, we didn't have anything on line 2. All of our loads were on A and C, so there's nothing there. Now, line 3 squared is going to be only 4,000 VA or 4 kVA because that's all we put on that one. We only had 3 4 kVA loads. We put 2 of them on line A and 1 on C. So let's do 4,000 divided by 120. And that is 33.3. Now, in this case, I'm going to drop the 0.3 because we're actually rounding up in the first one on line 1. So it'll work out, and it's not going to make a difference for our calculation. So we're going to use 33, and it allows for me to use more rounded numbers. All right, so it's 33. So the first part of this equation is line 1 squared, which was, in our case, 67, okay, squared. Line 2 squared, which is 0 squared, and line 3, which is 33 squared. So what does that work out mathematically? So that would be 67 squared is 4,489. So you write that down. That's the first one you write down. The next one we had was 0 squared. That's actually nothing, so that's 0. And then the last one on that first part of the equation was line line 3 squared, and we determined that was 33. So it's 33 squared, and that is 1,089. So the first portion of this formula, okay, or the brackets, so the first parentheses would be 4,489 plus 0 plus 1,089. That is 5,578. So you write that down. So that is on the left side of the minus symbol of this formula. Now let's work the second part of this. So that second part says, okay, what is line 1 times line 2? Okay, well, line 1 in this point is we're saying, okay, what was the line 1 current that we're dealing with? All right, that's the value that we're dealing with here. All right, so let's start working it out. So line 1 was 67 times line 2, which is 0. So 67 times 0 is 0. So 67 times 0 is 0. So that's the first one. The next one, it says plus line 2 times line 3. Well, line 2 was 0 times line 3, which 33 is 0. So it's 0. Okay. And then, of course, the last, and that's plus, and the last one is line 1 times line 3. So line 1 was 67 times 33. That is 2,211. So you write that down. Okay. So the first part of our equation was 5,578. The second part of our equation was 2,211. So let's work the brackets before we do anything with the square root. In this point, it is 5,578. Let's work it. 5,578 minus, we're following exactly how the formula says, 2,211. 2,211. Okay, that equals 3,367. Now, go to your calculator. You do the square root of 3,367. So in my calculator, I'm going to do the square root symbol, and I'm going to do 3,367, and that results in 58.02 or 58 amps. That's what I'm dealing with. So in this equation of that load that we're dealing with between phase A and phase C, because that's the only one that our neutrals are connected to, my maximum unbalanced load based on this scenario here is 58 amperes. Okay, so that is the maximum unbalanced load, the actual current, if you will, that will be seen by that grounded neutral conductor. Okay, so that's how you balance it out, and that's what our neutral load is. Remembering again that we do have rules for neutral conductors, minimum sizes. We have to understand the concepts of 250, 102C1. We have to understand our usage and how we're using it, but that is how you're going to calculate the maximum unbalanced load, okay, on that transformer. Okay, that's the maximum neutral load that you're dealing with. All right. Okay. Now let's go on and do a delta and work a delta out. We'll use this. We'll see if these same scenarios work out and how we're doing that. Okay, so let's do a scenario here. Again, it's a multi-step process, a little bit shorter, not as complicated as dealing with the WISE part of it. But it's still something you're going to do. So I'm going to give you some scenarios again. We're going to do the delta. Now, in this case, we're going to use a delta secondary with a center tapped C phase. And so we're going to call that C1 and C2. But really, we're going to have one half of it is going to be like connected to line 1, and the other half is connected to line 3. Because that C phase is between line 1 and line 3. Okay, that's the phasing that you're getting. Okay, so we're going to kind of do that scenario, and we're going to try to balance it out. All right, so let's kind of work it. So let me give you some values. You're going to write these values down. They're going to be kind of the same values we used before, but obviously different voltages to utilize what we need to do here. So I'm going to give you a 42 kVA, 3-phase, 240 volt load. And this purely is a 3-phase application. It's going to utilize A, B, and C. I'm going to give you two 12 kVA, single-phase, 240 volt applications, which again are going to utilize the application of phase A and phase B application. Okay. And then I'm going to give you, I'm going to give you 3 4 kVA single phase 120 volt loads applications. All right. And that's how we're going to utilize it. All right. So let's kind of look and see how we do this. Now, just like before, I'm going to create a column. But what I'm going to do is I'm going to create 4 different columns, or you could have 5 different columns. It's perfectly, it doesn't really matter. But you need to have the column for phase A, phase B. Then you have a column for C1 and C2. And then, of course, you can have the total if you want to add them up to, whatever, to the left or to the right, whatever you want to do. All right, so I gave you the 3 different loads that we're working with. Okay, the first thing we need, again, as always, what we've already done is we've configured whatever our loads are. And we're going to break these things down into the VAs because we need to balance this thing out. So I always think it's easier to break it all the way down into the pure VA. So take whatever your KVA is and multiply it by 1,000 in order to find out what your VA is, and then plug those values in there. But we'll just kind of work it. It doesn't really make a difference in what we're doing. All right, number 1, again, determine your VAs. Again, we're doing a delta-delta. In this case, it's a delta secondary with a center-tapped C phase in order to derive us the 120s. Okay, it's important to remember that. All right, now I need to balance the load on this transformer. Number 1, 3-phase loads. Again, all of those loads, we start out with the top. The 42 kVA, it is purely 3-phase. It's going to utilize all of the legs here. So we distribute that evenly. Always remembering that phase C is now broken into C1 and C2 because it's 2 parts to that winding. There's a left side and there's a right side, if you will, theoretically speaking. Okay, so we want to remember that. So let's kind of do it here. So we had 42 kVA, which is 42,000 VA. We're dividing that by 3. That is 14,000 VA or 14 kVA. So phase A, I'm putting 14. Phase B, I'm putting 14. And then for C1 and C2, I'm going to break that in half. And I'll put 7 under C1 and 7 under C2. Ultimately, that is still C phase. But I'm just going to show you how we break that down. Okay? All right, so C1, C2, 7 to 7. Ultimately, that's 14. And you get 14 kVA or 14,000 VA equally distributed amongst the A, B, and C. All right? Okay. And that's our total 42,000 VA. Next thing we've got is the 240 volt single phase loads. Now, we put 100% of those loads on phase A or B. Okay? So, again, reminding you that it might be okay to put those on C, but we got to remember that C is going to carry the balance of our 120 volt loads. So, if we had to move something around, then we can do that if necessary in order to be able to achieve that. But we have to make those connections. So, we just have to keep that in mind. So, as far as we're concerned here, our case was we had 2 12 kVA applications here. Yeah. So what we're going to do is we're going to put under phase A, we're going to put 12 kVA. Remembering that that's actually going to be line 1 and line 2. It's what you're going to make the connections in the panel. Okay. We're balancing right now, but in the panel, you would use line 1, line 2 for this one. And then for the other one, we're going to put the 12 kVA under phase B, which is utilizing legs L2 and L3, okay? But as far as our columns, remember, we're balancing out the transformers. So as far as that goes, we're going to put 12,000 VA under phase A column and 12,000 under phase B column. Just remember that A is utilizing line 1 and line 2, and phase B is utilizing line 2 and line 3 when we actually go to terminating these on the panel, in the panel board. Just remember that. Okay. Now, that's what we did for those applications there. So we have it on phase A, which is utilizing line 1, line 2, phase B. So just kind of keep those scenarios in mind. But as far as our concern for balancing, we're putting it 12 on A and 12 on B, and we're not putting any of those. There's only 2 of them. We're not putting that on C. Okay. Now, if I needed to put it on C in order to balance out this transformer, that's okay. Remember, we're dealing with a phase-to-phase application. Okay. It's not going to get you 208 in this scenario. We're going to get 240. Don't worry about it. You're good to go. Now, let's go on now to when we're dealing with those 120s. Now, on those, I put 120 volts 100% on C1 or C2. But remember, that's utilizing the C phase only because that is the one that we're going to put these loads on. Okay? And we're trying to balance it out. Because at this point, we don't really have anything really placed on there except for the 7,000 VA that we did for balancing out that 42 kVA load. Okay, we did the 7 and 7. It's 14, but we balanced it between C1 and C2 because ultimately that's one whole winding itself. We're just breaking it down in our table. All right, so in doing that, it's just as simple. Now we come down and we take the, in what we were dealing with in our delta configuration, we're going to take it was 4 kVAs. So I'm going to put under C1, I'm going to put 2 of them because I got 3. I'm going to end up putting 2 under 1 anyway. So I'm going to put 2 of them under C1, which is going to be 8 kVA, and I'm going to put 1 of them under C2's value for the kVA. So I'm going to put 4 kVA or 4,000 VA under C2. Now, ultimately, this is still all considered the C phase, but we're breaking them out because we're going to need that to do that when we start doing the unbalanced load for the neutral calculation. It just makes it simpler to do that. Okay? All right. So let's add them up here. So what do we have under phase A? 14 plus 12 is 26 kVA or 26,000 VA. Okay, that's pretty good. Now let's look at B. What do we got? Well, it's 14 plus 12 again. So that's 26 kVA or 26,000 VA. So we're looking good. So what is C1's total? Well, C, we had a 7 on C1, and then we had the 8 that we put on it, okay? So that equals 15, all right? And then we had C2, which had 7 on it, and we're adding the 4 kVA that we just placed on it. That equals 11. Now, collectively, we can add that all together now, and that tells us what our phase C actually is. All right? So, that point, it's going to be 15 plus 11. And so, what we've got is 26 kVA. Okay? That's what we ultimately have at this point. Okay? So, all right, let's see here. So, but at that point, you would say, okay, it's 26, 26, and 26. It's balanced. But there's something to remember. When you're sizing the transformer, you want to take, if you're dealing with the C1 and C2 in our example, since we're talking about a C transformer, you want to actually use the largest value. Whichever side of C1, C2 results in the larger, you take that value times 2. You don't just add the two together. So in your mind, you would say, well, it's 26, 26, 26. I took 15 and 11. But in reality, when sizing, we want to take C1 because that was 8. And we want to do that times 2. And that is the value that we're adding. Okay? So in our case here, that was 8. Okay? Let's see. 8 plus the 7. So that was 15, right? So we want to take that value and double it. So we take the 15 times 2, and that is 30. So what we have really for sizing our transformer is a phase A at 26, phase B at 26, and a phase C at 30. Okay? Very common mistake. People want to add C1 and C2 up, but you want to take the larger of the two. Okay? So in this case, 15 on C1 was larger than the 11 on C2, so we take the 15 and do that times 2, and that's what we're going to use to size this transformer. So at the minimum, I would need a transformer with a phase C winding that was at least 30 kVA. Okay? Ultimately, this is probably going to result in a 30-30-30 or a 90 kVA, or some people that are sizing for capacity and realizing they might have other loads that need to be the 120, they might go up to 112.5 kVA drive type transformer, and they might do that as well. Okay? All right, so that's the concept. So I wanted to explain to you how you do it, but then don't fall into that trap where you go, it's C1 total plus C2 total, and you just add them together. No, you need to take the larger, okay, of C1 and C2. Okay? Ultimately, since that is only one transformer, that's the one that you need to worry about as far as the configuration. All right? All right, so we've dealt it, we balanced it out, we've done everything. Our loads, our 120 volt loads were placed on line 1 and on line 3 of dealing with the in the panel, because line 1 and line 3 are the ones that are ultimately going to put us on that C transformer, that C winding. The size of panel board and the conductors, you have to balance the loads in amperes. So then we need to convert these values down to what the amperes would be. And if you have the kVA, then you can convert it down. And we did this in our series where we can take the kVA and we can convert this and we can find out what the actual current is on it. And that's what they're going to use to size conductors and whatnot in that scenario. All right. Now, what about the delta neutral current? Okay, how do we determine that in this scenario and what we just did? And in our case, when we're doing the neutral current formula, it's neutral current equals the line 1 current minus the line 3 current. So in our case here, the neutral loads that we had was 8 kVA on line 1 and 4 on line 3. Okay. So you take the values. Now, in order to do this, again, you have to get the amps. You have to formulate, you have to calculate it out to get you the current. So in our case, line 1 was 67 amps and line 3 was 33 amps. So you take the 66 minus the 33 and that results in 33 amps. And that is what your neutral load is on this delta scenario. Okay? All right, so that's a formula. Remember that no neutral load is connected to line 2. That's the high leg. Why? Because that would be 208 volts. You wouldn't utilize that. So always remember in that scenario, because you saw us go through this and we didn't really talk about the B leg and everything. You're using that leg for your 3-phase. You're using that leg for your single-phase 240s, but because you're going phase to phase, but you're not utilizing the high leg to any neutral loads in that scenario. That is a high leg. It's got to be marked accordingly. It has to be identified at the panel board. All of those type of scenarios. Again, the maximum imbalance load is the actual current on the grounded neutral conductor. And we just showed you how you figure that out in our example here. Yours might be different. That's how we do the example there. Okay? All right. Pretty simple to balance this out. Just remember that this information really does carry over into sizing the panel, or how we lay it out in the panel board. Also remember that in our case here in this delta one, which was 26, 26, 30, it could be 3 individual 30 kVA transformers, or it could be a 3-phase 90 kVA transformer that could be utilized. Okay, really. You could create this same thing with 3 individual single-phase transformers depending on how you connect them. That's what you see out on utility poles all the time. Or you get the dry-type transformers that we usually see, that this is all already done within itself. Okay? It's a 3-phase transformer. Okay? Other than that, guys, I really think that about as much that we should probably cover in this series, 2 parts. I do encourage you to go back and listen to part 1. But if you want to get more detail on how to size the primary and secondary transformer current rating, you want to go watch our video series on our YouTube channel, or you can get there from our website. If you want to learn how to size the overcurrent protection device for the primary or the secondary windings of a transformer, go watch that video. It's a multi-part series as well, and it can give you a lot of insight on dealing with transformers. We don't cover every possible scenario, but we cover a large amount of information in that series that you can get a lot out of it. So hopefully you got something out of these 2 podcasts. Again, my whole effort is to try to teach you how to do these things as simple as possible, not to overthink it, not to make it more complicated than it needs to be. Sometimes people will agree and disagree with certain aspects of it. That's perfectly fine. That's for your prerogative to do that. Again, I encourage you to watch the video series because I do show different formulas, and most importantly, that neutral current formula. I like to show that one as well because it helps people understand the complexity. And that formula for the Y neutral unbalanced load That's a pretty long formula, okay? Whereas, obviously, you can see the one that's dealing with deltas is not so complicated, all right? It is obviously more complicated when you're dealing with a Y scenario, all right? Okay, well, hopefully you got something out of it. God bless. Until next time, stay safe. And again, thanks for listening to the podcasts and share them with other people. Hopefully you get something out of it. Until next time, stay safe. God bless.
Every day, the future's getting closer. Every day, the future's looking bright. Every day is another beginning.